Hi, in the last video, we're talking about mass flow rate and volume flow rate. So in this video, I will look into some examples that's used for in this concept in thermodynamics. So for this problem, it said it's 134, giving us the pressure at 200 kilopascal, and the quality X is 40%, and flow through this diameter, that's 1.1 centimeter, and velocity is given. So I'm going to spell out velocity so you will not be confused with our small v as specific volume. That's 50 meters per second. So we need to find out what's going to be the mass flow rate. So the equation to figure out the mass flow rate we talked about last time, mass flow rate is going to volume flow rate divided by specific volume. So look at this equation. Do we know volume flow rate? Yeah, we also know volume flow rate formula is basically velocity times the cross-section area. We know the velocity and the geometry of this cross-section is given. It's a circular shape, and with the diameter d given as 1.1 centimeter. So we can certainly figure out the cross-section area. So we can find out velocity, volume flow rate. Okay. So let's go ahead and make that as our first step. Volume flow rate is going to be velocity, 50 meters per second, times cross-section area, which will be pi r squared, or pi d squared over 4. So d, we're using 1.1 centimeter, pi d squared over 4. Looking at this one, we needed to convert. So how about we convert our centimeter to meter. So 1 meter is equal to 100 centimeter. So we divide by 100, so move this decimal twice to the left. So we get that much meter, pi d squared over 4. And quickly put into the calculator, so what we got for our volume flow rate. So 50 times pi times 0.011 squared, then divided by 4. Okay, so we have 0.0, oops, what did I get? 0.00475, which is 4.75 times 10 to the power of -3. That's going to be our volume flow rate. Volume flow rate has a unit of cubic meter per second. Okay, so we have volume flow rate taken care of. So in order to solve this mass flow rate, going back to this original equation, the only thing we need to solve is this specific volume. Okay, how do we find this specific volume? Looks like we need to look at our 134 table. They told us the pressure, they told us quality. That tell us it's going to be a mixture, because you have a quality, which means it's have saturated liquid and vapor mix. Then, since it's a mixture, V, specific volume, is going to use in the equation as VF plus X VFG, which is VG minus VF. And we're going to look at the table. Okay, so here I have the table open up. This is refrigerant, and since we are given the pressure, so we're going to look at the pressure table, A12. So let's go to A12. And the pressure for this problem is 200 kilopascal. A12 and 200 kilopascal is going to be right here, right? It's going to be right here. 200 kilopascal. And we needed to read VF. So our VF is going to be 0. It's going to be this value. Okay, so it's going to be 0.0007533. Then plus quality is 0.4, which means 40% are saturated liquid. Then Vg minus Vf. Vg is going to be this value. (0.083897 minus VRVF. Oh, I think I got the wrong value. It's going to be this value. So it's going to be 0.099867 minus VF 0.0007533. All right, so when you put all those numbers in there, I have answer as 0.0404. That will be giving us a unit of meter cube per kilogram. So we know now the specific volume as well. We can go back to this governing equation to find our mass flow rate. So the last step, mass flow rate is going to be equal to volume flow rate divided by specific volume. The volume flow rate is 4.75 times 10 to negative 3 meter cube per second, and volume flow rate is 0.0404 meter cube per kilogram. So meter cube cancel out. Flip the kilogram to the top, we get our unit for mass flow rate is kilogram per second. So now let's put into calculator. 0.00475 divided by 0.0404. Then the answer is 0.117 about. Okay, so that's the answer for the mass flow rate.